We are to show that the limit as x tends to infinity of 1 plus 1 over x, all this raised to the power x, is equal to e, where e is the exponential constant. E is approximately 2.71828. It is an irrational number. For us to show this limit, we are going to make use of the fact that e raised to the power ln a is equal to e. There is a video we did the proof of this. You can search for that video in this channel. You watch, you learn so much. If we take e raised to the power ln 1 plus 1 all over x, all this raised to the power x, applying this formula, this is our e, it will simply be equal to 1 plus 1 all over x, all this raised to the power x. It simply means if we take the limit as x tends to infinity of 1 plus 1 all over x, all this raised to the power x, it will be equal to the limit as x tends to infinity of e raised to the power ln 1 plus 1 all over x, all this raised to the power x. By applying the law of power of logarithms, we are going to bring this power in front of ln 1 plus 1 over x. This will simply be equal to the limit as x tends to infinity of e raised to the power x ln 1 plus 1 all over x. This will simply be equal to the limit as x tends to infinity of e raised to the power x. Remember, you can express x as 1 all over 1 on x. If you take the reciprocal of 1 over x, it gives you x. So this will give us the ln of 1 plus 1 all over x all over 1 on x. As such. Now, by applying the properties for limits, we are going to bring up this limit here. This will simply be equal to e raised to the power the limit as x tends to infinity of ln 1 plus 1 over x all over 1 all over x, by applying the properties of limits. Now we are to find this limit, the limit of this power, the limit as x tends to infinity of ln 1 plus 1 over x all over 1 over x. If we go directly by direct substitution, this will simply be equal to ln 1 plus 1 on infinity all over 1 all over infinity at the denominator. This will simply be equal to the ln of 1 plus 1 all over infinity, that means we are dividing 1 by a very, very large number. So this goes to 0 all over 1 over infinity gives us 0. This will simply be equal to the ln of 1 all over 0, which is equal to ln of 1 gives us 0 over 0, which is the indeterminate form. That means it is meaningless, and when we have 0 over 0, there is no conclusion, there is nothing we can say about the limit of this function. So we are going to apply other techniques of getting the limit. In this case, we are going to apply L'Hopital's rule to get this limit. And L'Hopital's rule states that if we are to take the limit of a rational function, let's say g of x all over f of x as x tends to infinity, if by direct substitution this gives us the indeterminate form, that means 0 over 0 or infinity over infinity, then this limit will simply be equal to the limit as x tends to infinity of g prime of x all over f prime of x, where g prime of x is the derivative of the function g of x with respect to x, and f prime of x is the derivative of the function f of x with respect to x. This is L'Hopital's rule. We are going to apply L'Hopital's rule to find this limit. The limit as x tends to infinity of ln of 1 plus 1 over x all over 1 over x is simply equal to the limit as x tends to infinity of the derivative of the function we have at the numerator, this d over dx of ln 1 plus 1 over x all over the derivative of what we have at the denominator, d over dx of 1 on x. Next, we are to differentiate the numerator and the denominator before finding the limit as x tends to infinity. Let's perform the differentiations. Differentiating the numerator, d over dx of the ln of 1 plus 1 over x is simply equal to, we are differentiating a ln function, and the derivative of this function will simply be equal to, we are going to differentiate what we have in the bracket, then we divide it by what we have in this bracket. You can watch our videos on how we differentiate natural logarithms. There's a video I did on this. This will simply be equal to differentiating this d over dx of 1 plus 1 over x, then we divide the derivative by 1 plus 1 all over x. And this will simply be equal to differentiating what we have in this bracket. The derivative of 1 is 0 plus the derivative of 1 over x. Remember, 1 over x can be expressed as x raised to the power negative 1. Differentiating x raised to the power negative 1 gives us negative x raised to the power negative 1 minus 1. We have to divide this by 1 plus 1 over x. This will simply be equal to negative x raised to the power negative 1 minus 1 is negative 2 all over 1 plus 1 all over x. X raised to the power negative 2 is simply the same as 1 all over x squared. This is what it means. We are going to bring it down, so this will be equal to negative 1 all over x squared times 1 plus 1 all over x as such. This will simply be equal to negative 1 all over multiplying all through x squared times 1 gives us x squared plus x squared times 1 over x gives us x. This is the derivative of the function we have at the numerator. Next, we have to differentiate the function we have at the denominator, that is the derivative of 1 over x, d over dx of 1 over x is simply the same as d over dx of 1 over x can be expressed as x raised to the power negative 1. This is it. This will simply be equal to differentiating this. We multiply by the power, which is negative 1, gives us negative x, the power negative 1, then we subtract 1 from the power. This will simply be equal to negative x raised to the power negative 2, which we can express as negative 1 all over x squared. This is the derivative of what we have at the denominator. Now, knowing the derivative of the function at the numerator and the derivative of the function at the denominator, we can now proceed to find the limit as x tends to infinity of the given function. The limit as x tends to infinity of ln 1 plus 1 over x all over 1 all over x will simply be equal to the limit as x tends to infinity of the derivative of the numerator. The derivative of the numerator gives us negative 1 all over x squared plus x. We divide this by the derivative of the denominator, which is negative 1 on x squared. This will simply be equal to the limit as x tends to infinity. We are dividing two fractions. We are going to maintain the first fraction, negative 1 all over x squared plus x, times, we invert the second fraction, the numerator becomes the denominator, times x squared all over negative 1. This will simply be equal to the limit as x tends to infinity of negative 1 times x squared gives us negative x squared all over x squared plus x times negative 1 gives us negative x squared plus x. Negative x squared divided by negative x squared plus x, you see that the negatives will cancel off. This will give us the limit as x tends to infinity of x squared all over x squared plus x. By making use of the techniques of finding limits, at the denominator we are going to factor out x squared. This will give us the limit as x tends to infinity of x squared all over factoring x squared in the denominator gives us x squared times 1 plus x squared times 1 over x gives us x. Close the bracket. You'll see that x squared in the numerator will strike off x squared in the denominator. And we will simply be left with the limit as x tends to infinity of 1, and the numerator will be left with 1 all over 1 plus 1 all over x at the denominator. At this level, we are going to replace x with infinity. Replacing x with infinity, the limit will simply be equal to 1 all over 1 plus 1 all over infinity. This will simply be equal to 1 all over 1 plus 1 all over infinity gives us 0. That means we are dividing 1 by a very large number. So this will be 0. And this will be equal to 1 all over 1 plus 0 gives us 1. 1 divided by 1 is equal to 1. It simply means the limit as x tends to infinity of the ln of 1 plus 1 over x all over 1 all over x is equal to 1. Knowing this, it simply means e raised to the power the limit as x tends to infinity of this of the ln of 1 plus 1 over x all over 1 over x is simply equal to e raised to the power, this limit gives us 1, e raised to the power 1. And e raised to the power 1 is simply equal to e. Remember from the beginning, we started by establishing the formula which shows that the limit as x tends to infinity of 1 plus 1 over x raised to the power x is equal to e raised to the power of the limit as x tends to infinity of the ln of 1 plus 1 over x all over 1 all over x. From this, it simply means the limit as x tends to infinity of 1 plus 1 all over x, all this raised to the power x, is equal to e, which is what we have to show. Then we conclude, therefore, the limit as x tends to infinity of 1 plus 1 over x, all this raised to the power x is equal to e. We are done with the solution of this question. If in case you have any doubts or any worries, feel free to drop your questions at the comment section. Please like the video, share, and subscribe to this channel. Thank you very much for watching.